Hi guys, my name is Alex Guillerez, and I am here to present my undergrad thesis, which is about trace element signatures of magnetite crystallized from magmatic salts, done at the University of Toronto. So first, my research is about iron oxide apatite deposits, which are iron deposits that are mainly composed of magnetite and apatite. And these deposits are enriched in rare earth elements and abundant in critical minerals, which obviously hold an economical importance, and we'd like to know where to find them. Magnetite's a useful mineral to analyze because it's present in a wide variety of deposit types, and we can very easily measure ranges of trace elements using LA-ICP-MS. And these iron oxide apatite deposits they vary heavily between locality in terms of age and composition, and the scientific community has not agreed on a common formation condition or petrogenesis. A bit of past work that's influenced this study. First off, we have a study by Sarah Dare et al. In 2014, who used trace elements in magnetite as a petrogenetic indicator. And this figure from her paper distinguishes between titanium and nickel over chromium content, and it defines a clear separation of magmatically formed magnetites and hydrothermally formed magnetites. And it's worth noting that some IOAs were measured for this study and were found to plot under the hydrothermal section of the graph. Next off, we have two studies by Wyatt Bain et al. In 2020 and 2021, who found fluid inclusions, carbonate sulfate melt inclusions within IOA samples, and then theorized that they may be formed like a magmatic salt when fluid causes partial melting of the evaporites, which would enrich the magnetites through assimilation to the level of trace elements they're known to have. This is a very unique observation, and it's safe to say that this motivated our study, and we decided to approach the question more experimentally. Our objectives for this study is to use trace element data to evaluate the formation of IOA deposits, and we're going about this in two ways. Half the study is about natural samples, and the other half would use piston cylinder experiments. And at the end of the study, we would love to be able to answer if magmatic salts are effective at transporting iron, and is there a distinctive and measurable trace element signature between the magnetite phase and a salt phase. So first, the natural samples. Our natural samples from the U of T collection included magnetites of a variety of different formation conditions that we were able to find within the collection. We did this to establish a comprehensive data set that we could compare our own IOA trace data results to. So these natural samples were cut, cast into epoxy, and measured with electron probe to find the major and minor elements, and then used that to standardize results for ICP-MS, which measured the trace elements. And we identified three major phases in our iron oxide apatites: magnetite phase, ilmenite exsolution within the magnetite, and apatite. This image here is a backscattered electron image of an iron oxide apatite sample collected in Chile at Sosita mine. We analyzed magnetite from a variety of different backgrounds because, again, to establish a comprehensive data set and to compare our IOA trace elements to magnetites with a magmatic formation or even a hydrothermal formation. Since we also ended up using literature data, we decided to include the ilmenite exsolution in the magnetite analysis, as was done in previous studies, like in our literature data, to better to get a better comparison between our data and the literature data. And we also did analyze other phases we found within these magnetites, but they're not very relevant to what I'm talking about today. Our samples that we analyzed are mostly recently formed Chilean ones or Chinese ones found in the North China Craton. We were also donated some American samples from the Buena Vista deposit in Nevada and the Iron Springs Formation in Utah. It's worth noting that even within iron oxide apatites, the Chilean samples are unique in their age and tectonic condition, since they date from the Chilean iron belt, which was formed in the Cretaceous period. And we are trying to collect data from a variety of tectonic settings and ages, which is why both Chinese Cratonic samples and Cretaceous samples were included within our study. And here's the results of our natural sample analysis. The left is our data overlain on top of Dare's figure. The IOA data tends to plot on the hydrothermal side. However, some does plot on the magmatic side, and there's no real clear distinction. It's also worth noting that we see this again with our carbonatite, which is comparable to the magmatic salt Bain theorized that IOAs could be formed like. And on the right, we see this orange line represents the bulk crust niobium over tantalum ratio. And we plotted our measured samples on top of this. And something we noticed is that the IOAs exhibit the highest variance among every different magnetite group, even though niobium and tantalum are very similar geochemically and thus should behave the same. So yes, they're geochemical twins and thus difficult to fractionate. The similarity of niobium and tantalum, such as the same ionic radius and charge, mean they tend to behave the same way geochemically, and should be difficult to fractionate, and they shouldn't exhibit large fractionations like we see in some IOAs, such as these ones. Now, it's worth noting that not all of our IOAs exhibited a high fractionation, but they did exhibit a higher fractionation than anything we would find in magmatically or hydrothermally formed magnetites. They've begun to look into this, why this is, and found that a study by Wechsler et al. In 2012, they reported that salts may be able to fractionate them, where niobium is 10 times more compatible in molten salt than tantalum would be. It's something we'll have to look more into, but for now, that is interesting and something to note. Next, we have our high field strength elements graphs, normalized to bulk continental crust. The IOA magnetites here seem to exhibit a lower than average range of high field strength elements when normalized to the bulk continental crust. This figure also shows the elevated niobium over tantalum ratio that is seemingly exhibited by IOAs. And when we compare these to the magmatic silicate magnetites over here and our carbonatite and porphyry deposits here, these two are typically thought to have hydrothermal origins. And as we can see, the IOA graphs show a much more restricted range and are pretty distinct even when just looking at the pattern. However, they do bear some similarity to some carbonatite samples, not all, but some. And we're so far thinking that this may be a mineral phase within carbonatites that acts similar to an IOA, something we'll have to look into more, especially with our experimental samples. This is all very interesting, however, nothing conclusive so far. And onto our experimental methods. We are using a piston cylinder to determine how soluble magnetite is within carbonate sulfate melts, and determine the trace element partitioning between the magnetite phase and the magmatic salt phase and carbon. So we equilibrate magnetite with molten carbonate sulfate mixtures and then analyze the run products by electron microprobe and LAICPMS. And it's worth noting that the experimental side of this study has really been done by Zhongjing Yuan, the PhD student, who's done a great job so far. We're trying to measure the solubility of magnetite with the salts. This picture shows the magnetite and the salt in equilibrium, and thus the trace element partitioning can be measured between the two phases. So here in this very light gray is the nickel capsule that just encapsulates our experiments. And this medium gray is the magnetite powder we put into the capsule. And this dark gray, which shows a very fine grained texture, is the quenched melting of carbonate and magnetite together, meaning that the two phases should be in equilibrium. And our next step would be to measure the experiment under LAICPMS to get comparable trace element data within the compare it to the natural samples. Very, very preliminary analyses show that iron content of the melt decreases as sulfate content of the starting material increases. So we've been going about this by mixing in different weight percents of sulfate and carbonate. And it seems like the more sulfate we add in, the less iron that is in the quenched melt specifically. This isn't a we don't have enough data to properly interpret this yet, but it does show a good starting point. Over here is a carbonate sulfate melt. You can see there's some strange textures we've seen because of some interaction with the nickel capsule. But it's still being measured regardless. In summary, magnetite from our IOA deposits, our natural samples, do exhibit a wide range of niobium over tantalum compositions, which again can be more elevated than what we would expect for magnetite in general and when compared to other systems. High field strength element patterns are similar to those observed from some magmatic carbonatites, but are distinct from many samples that are considered to have a hydrothermal origin. Experimental procedures are underway, and hopefully we determine some magnetite solubility in the melts and eventually move on to trace element partitioning to be able to compare our experimental samples to our natural samples. And I'd like to thank the PhD student, Zhongjing Yuan, who I've worked with very closely on this, Colin Bray Yanan for assistance with the machines. Our American samples were donated by Matthew Steele McInnes. We thank him very kindly for that. My two thesis supervisors, Corliss Seo and Neil Bennett, helped me so much with this. And this was funded by NSERC, and thank you to Mineral Deposits Division for letting me present.